Good afternoon, everyone. Let's discuss computational capabilities of our oscillators under weak local Kuramoto-like coupling. Coupled oscillators appear in many branches of science because of the wide range of dynamics they can display. They can simulate systems going from mechanical instances to more sophisticated electrical signals to even social structures. Historically speaking, Wiener took the first steps when studying alpha rhythms in the brain, but it took a rather complicated approach to it. A big breakthrough came with Winfrey's PhD thesis proposing the weak coupling approximation, and later on Kuramoto formulated one of the more studied models in this context. But most of this work have been done in global interactions where you can do a sort of mean field approximations. When the interactions are local, there's less agreement in literature, with works from Sakaguchi to Daido arriving to often contradicting conclusions. So these motivated our group to adventure into these locally interactive system context to try and gain more insight in how does the coupling and topology can impact the long-term dynamics of such models. We went ahead and chose the Adler oscillator, which is a well-known equation. And the observable in these kind of models, it's always a periodic function of the phase called often activity of the oscillator. We went ahead and chose sine function. There's two parameters of the model, omega and gamma, which play the role of a sort of a natural frequency and a self-feedback parameter, respectively. And the model is known to have a Saronov bifurcation for a given gamma when changing omega. The thing is that when you couple these oscillators, the physics of it change. Our group has previous papers studying the influence of several couplings and topologies in it, and we just recently proposed a local Adler-Kuramoto coupling, which is taken to be proportional to the sign of the phase differences between immediate neighbors. So it's happening at a local scale, and periodic boundary conditions are imposed. We recently published the analytic treatment of such a model, and we found that global coherence or phase synchronization is possible. So it's a steady state where all oscillators end up at the same phase value depending on the parameters value. So it's a phase synchronization state with an existent condition of omega lower or equal than gamma. So basically the diagonal in parameter space is the existent curve. However, the stability region of this synchronized state, it's limited to a portion of parameter space, and it's actually not the same as the bifurcation curve. So there is a portion of space where the solution is possible yet not stable, and this poses a possibility for more complex patterns to form. How could we inspect such patterns? Through a visualization method. Such method could be taken as the binarization of the states. So let's suppose we have the configuration of the system at a given instant. We could build a matrix where each row is the settings of the n oscillating units, and time runs downwards. So you end up with a real value matrix, which can be further binarized, taking the mean activity as a threshold value. Then you can plot such matrices like these, where each white pixel is a 0 and black pixel is a 1, and the patterns that emerge resemble those found in cellular automata, which are systems known to have computational complexity. So the fact that they resemble each other could be an evidence that oscillating systems themselves have computational complexity. Now, you can actually move along parameter space and find different kinds of patterns like those, but you also can find the similarities between some corresponding automatas. The worst agreement here is found from gamma equal 1.8, which has wavy-like patterns, which you don't really see in stellar automata. But the agreement is pretty decent, even though it's a visual inspection. We could try and go a little further ahead and quantify this similarity. To do so, we go back to information theory. And we'll be using entropy-based measures, specifically the entropy density as a measure of unpredictability in a sequence, and the excess entropy as a measure of correlation in all scales in such a sequence. They are complementary measures, but their extreme values are not compatible with a computational task. If you think or if you expect for a system to have computational complexity, you would expect it to be able to do three basic tasks, namely receiving, storing, and transforming information. Now, let's say you have an extreme maximum value of entropy density. That means that no matter what information you give to the system at the beginning, it's going to evolve to an absolutely random state. The other extreme would be a zero entropy density, which would be an indication of a trivial state. So no matter how complex the information is at the beginning, the system will evolve to a trivial configuration. And a similar argument could be made in the case of the excess entropy. So intermediate values of both would be taken as an indication of computational capabilities. With that in mind, our group has several previous papers using these measures to quantify complexity in the context of nonlinear systems. Here we were able to build these plots I'm showing you, where rho is the symbolic density as well, density of ones in the final state. And you can actually pinpoint in these plots the different oscillators and automata we were looking at before. So the dashed line is the oscillator corresponding to gamma equal 1.0 and omega equal 2, of course. And the solid point corresponds to the corresponding automata. The closest solid point is to the curve, the more similar they are in the context of entropic-based measures. So you can see that the agreement in this case is pretty decent. When you move ahead to gamma equal 1.8, the agreement is way worse because of what we knew before. There's no really wavy patterns in the context of cellular automata. So you can expect that the agreement would be worse in this case. It gets better when you go to gamma equals 2.5 approximately with these triangular patterns in both oscillators and automatas, and also in the stable region where they both end up in an homogeneous configuration. So this is a quantitative confirmation of this visual similarity between the two systems. And one could argue, if they are able to sustain similar patterns, one could expect that the computational complexity would also be similar. So that would be a first result. Now, we also have some extra features here that are interesting. We can change the way we are plotting and see this sudden point or increase, in excess entropy, which could be indicating a sudden increase in computational capabilities, which is actually compatible with the EOC hypothesis posed or proposed by Langton in the 90s, which is relative to the sudden enhancement in computational capability in the vicinity of highly sensitive regimes, mainly chaotic regimes. Our team has previous papers as well, verifying these hypotheses in different nonlinear systems. And we could actually test if this is actually happening in the vicinity of a highly sensitive regime. To do so, we went ahead and used algorithmic distance. So we perturbed the initial settings in our simulations and determined how far or different, algorithmically speaking, were the evolutions of the system. And that's what I'm plotting on the top of the plot. So that allows us to actually check that indeed the sudden enhancement of computational capability happens in the vicinity of a highly sensitive regime. So indeed, we are in the presence of a verification of the EOC hypothesis in the context of locally interacting oscillating systems. Furthermore, when you do the matrix of these points, it's not evident that the computational capability has increased. However, these entropic-based measures are able to capture this process. So as the main conclusions or takeaways of this study is to make an argument about the presence of general computational capabilities in systems of coupled oscillators, even in their simplest formulation and topology possible. We did not only this is verification in a qualitative way, but also in a quantitative way, relying on these entropic-based measures of computational complexity as perspective for these studies. We want to explore effective topologies appearing in computational space through this algorithmic distance we discussed. We built adjacency matrices, and we saw non-trivial configurations in computational space, result that it's also just recently published. But we also did a zoom in the matrices using our previous results in several automata. And we found out that these triangular patterns and wavy patterns actually are built of basic blocks of information that appear at a local scale and are affected by the system. They are actually a finite amount of blocks of information, and the system kinds of does computations with them. They actually we track them in the evolution of the system, and you can actually detect transitions between them and collisions. So we are expecting to develop somewhere viewing the system as a computational system, which affects these finite alphabet and does task upon this alphabet. And last but not least, since we are discussing this computational capability of the system, it would be good to be able to do some meaningful computations with them. The idea would be to have a computational workbench where we have an input, a computational capable item or entity, which give us an output. And the idea is how can we link or insert these oscillating systems into the computationally capable entity. So those are the three fronts we are planning on attack in a short future, and that's all we have for now. Thank you.